This is the third video in a series about linear algebra. The first video is about vectors and bases. The second is about how to write a matrix by looking at what it does to a basis. I recommend that you watch those first because you'll need that for this one. Matrix inverses are something that get a lot of attention in a linear algebra course. There are all these formulas thrown at you, like for the determinant, the rule for inverting 2x2 matrices, Cramner's rule, the inverse of 3x3 matrices, etc, etc. These formulas and everything are important, but I think that they can obscure the very, very simple idea behind what an inverse actually is, and that's what we're going to get to now. An inverse is just what it sounds like. It's a transformation that undoes or inverts some other transformation. For example, let's think of a matrix A that rotates all the vectors clockwise by an angle. How do you get the vectors back to where they were? Obviously, just rotate everything back. And so A inverse rotates everything clockwise by the same angle. I want to write this as an equation. I'm trying to say that if you do A and then you do A inverse after that, it's like you did nothing at all. But how do I write do nothing as a matrix though? Well, let's use the usual method. Write down what it does to basis vectors. It takes the first basis vector and leaves it exactly as it is, and takes the second vector and does the same. This do-nothing matrix is usually called the identity matrix. So the inverse of A, if it exists, has the property that if you do A and then A inverse, it's like applying the identity matrix. But will require one more thing, that A undoes A inverse as well. If you apply A inverse and then A, that's also like you did nothing. You need to check both of these, as we'll see later. Now, here's a quick question so you can check your understanding. Imagine that you have these two basis vectors, and what your matrix does is it leaves the first one alone, and it sends the second one to the 0 vector. Does M inverse exist? Pause so you can think about it and put your answer in the poll. The answer is no. Let's try to understand why intuitively. Let's pick a vector, which in our basis looks like this. When we apply M to it, it just cuts the second bit off. What about another vector that starts off like this? Where does it end up? Also the same, right? Do you see the issue with that? Say someone gives you this vector and says it comes from applying the matrix to some unknown vector, and you need to find what that unknown vector was. This is the task that's given to the inverse matrix. But clearly here, our vector could have come from either one of these two vectors. So we can't say which was the original one. Since we can't undo the matrix, the inverse doesn't exist. Clearly, we can generalize this. The inverse for any matrix M doesn't exist if M sends two different vectors, v and u, to the same vector, since now you can't look at the result and figure out what the initial vector was. This is what I'm going to mean when I say a matrix loses information, since you can't look at a vector coming out of M and see where it came from. The inverse can only exist if M doesn't lose information. Here's another question. Imagine you have this matrix and it takes 2D vectors and makes them 3D by rotating the plane they're on into 3D space. Does this linear transformation have an inverse? Think about it carefully and then put your answers in the poll. Okay, so to start, if we have an inverse, it must be one that takes 3D vectors and makes them 2D. That's because it needs to take you from 3D back to 2D. And A is a nice matrix. It doesn't lose information. That's because if there's a vector that came out of A, you know where to put it back. Just rotate this whole plane back. You can find a matrix B that does that. So if you apply A and then B, it is the identity. This makes B what we call a left inverse. But the other equation, AB equals the identity, which means that B can be undone by A, isn't necessarily satisfied. And in this case, it's not satisfied at all. The problem is B loses information. Remember, B takes any 3D vectors and makes them 2D. Take a 3D vector that is not in the plane. Say B puts it here. But wherever it puts it, it's a problem because there's another vector that's already been sent there by B. In this case, it's this 3D vector on the plane that goes to the same place as our other vector. B loses information and hence it can't have any left inverse, i.e. it can't be undone, and so AB equals identity is definitely not true. So here's a question I want you to ponder. Is there any matrix that takes n-dimensional vectors to a smaller dimension S such that you can undo this matrix? In other words, can this matrix ever have a left inverse? The answer is that it can't. Here's a little proof of that. Let's say that there's some basis for our n-dimensional space. When you apply m to all of them, they end up as s-dimensional vectors. But they can't all be linearly independent anymore because there's too many of them. You can only have s vectors linearly independent from each other in s dimensions. So it must be possible to write the first vector, mv1, as a linear combination of the other ones. But m is linear, and so you can pull m to the front. This vector here is definitely not the same as v1, but our equation says m sends v1 and this vector to the same place. Hence, m loses information and so it cannot be undone. What we've just shown is that a non-square matrix, i.e. one going from a bigger space to a smaller space or vice versa, has no inverse. If it's from a smaller space to a bigger space, it might have a left inverse, but this left inverse itself goes from big to small, and so it can't be undone. What about square matrices then? We saw an example where a square matrix doesn't have an inverse, but how can we figure out if a matrix does or doesn't in general? Actually, for a square matrix, all you have to do is check whether m loses information or not. If it's lost, then sorry, you're out of luck, as we know. But if it's not, then m inverse does exist and it's really easy to find. Let's see why by just trying to create m inverse in the obvious way. Imagine that this is a basis for our space, and this is where m sends each of these vectors. We want m inverse to send these vectors back where they came from. Not only would that get the basis vectors themselves back, but it would get any vector back too. To see that, write any vector v as a combination of the basis vectors, and apply m to it. If our proposed inverse then took the basis vectors back, we also get v back as well. So we need to find a matrix that takes the basis vectors back correctly. If only mv1 to mvn themselves formed a basis, that would be perfect because we know what we want m inverse to do to that basis. And remember, we can define a linear transformation by just saying what it does to some basis. The only thing that would prevent this though is if they were linearly dependent on each other. say MV1 is a linear combination of the others like this. Pull M to the front. But this equation isn't possible because this means M maps V1 and this vector to the same thing, i.e. it loses information. So it must be that MV1 to MVN were in fact a basis. So we can go ahead and define M inverse as the thing that undoes M on this basis. Then M inverse times M is the identity. I want you to prove that M inverse also satisfies M times M inverse equals the identity. Write your proof in the comments, and that's your first homework. The second homework is to show that for a square matrix M, the condition that M doesn't lose information is the same as saying that the only vector M sends to 0 is the 0 vector itself. There is no other vector U that gets sent to 0. The reason I want you to show this is because if you've learnt linear algebra in class, you might have learnt a matrix is invertible if and only if the kernel of the matrix is 0, which is just another way to say this. I want you to see though that this is actually equivalent to the no loss of information condition, which I think is a bit more intuitive. As usual, there are hints in the description and I'd love to see your answers in the comments. Just give it a go even if you can't work it out completely. The next question is multiple choice. What is the inverse of this matrix? I know a lot of you have seen the formula for the inverse for the 2x2 matrix before, but let's forget about that for a second and try to do this question without it. The question is also in the description and there's a poll in the corner where you should put your answer. Pause the video now and try it because even though this is a homework question, I want to talk you through the answer of this one after you've had a think. Okay, so one way to do this is to just try each of these answers and see if it works. But let's do it another way. We know this matrix takes the first basis vector and sends it to the vector 1, 2, and it takes the second basis vector to 2, 5. So whatever the inverse is, it must undo this as we explained before. As you can see, that leads to these 4 different equations. You can solve the unknowns and find the inverse by A, substituting equations into each other, B, using Gaussian elimination, or C, getting your computer to do the Gaussian elimination for you. Doing one of these, you can see the answer is D. What I like about this question and questions on brilliant.org, who are this video's sponsor, is that they don't just give you a formula and then ask you questions where you have to plug numbers into that formula. That's what I found a lot of high school and early university textbooks do, and it's annoying because it doesn't teach you anything. Instead, they get you to do examples like this one and understand the principle yourself, then in the next few questions, lead you to finding the general solution on your own. This is exactly how I like to learn new maths. Before reading the proof of anything, I'll do lots and lots of simple examples first and try and understand the underlying reasoning. So I love how Brilliant allows you to do this in a structured way. They have loads of different maths and science courses on their website, which you can access completely with a monthly or yearly membership. If you follow the link in the description or on the screen, you can get 20% off the annual subscription. Alright, so that's all for this video. I hope you enjoyed it. The next one is about changing basis, which is key to understanding many things in quantum mechanics, including the Heisenberg uncertainty principle. It should be up here in about 2 weeks, and if you want to be notified, subscribe and click the bell button thing. Thanks for watching.